So I am going to speak about the mobile network generations followed by millimeter waves. Then if we go with millimeter waves, there are some disadvantages. One such disadvantage is there is increased free space loss, and followed by some techniques which can be overcome if we make use of millimeter waves, intelligent reflecting surfaces, millimeter wave antennas, then some of the fundamentals of antennas and the vision for the people of India, those are working in this particular domain. So when we want to discuss about this mobile network generations, particularly 5G or 6G, we have to have some info or idea about what is that we have been so far. The first thing is like we have evolution of the mobile, starting from 1G, 2G, 3G, 4G. Now we are in 5G, and there is a reason why we move from one generation to other generation. It's all because of increased data, and the technology is also changing. Along with the mobile network generation, we use different types of communication techniques. For example, 1G, we have used analog communication by FDMA, frequency division multiple access, and 2G is digital communication with TDMA and CDMA. Then 3G advanced CDMA, and 4G we are using OFDM and MIMO. And we will be using again a component of this OFDM, and much advanced OFDM is also being discussed to be used for the 5G, 6G communications. So if you could see in all the generations starting from 1G, 2G, 3G, 4G, and the 5G, the most important thing is data. So how much amount of data I can communicate, or I can be able to transmit or receive between the user equipment and the base stations plays a very important role. So what are the services offered by 5G? So now everyone speaks about, or the talk around the industry on the academicians is this 5G. What 5G offers actually? The EMBB, that is enhanced mobile broadband connectivity, then massive machine type communication, ultra reliable low latency communication. So if there is a question, are we experiencing all these advantages? Definitely no. We may have a better connectivity in 4G. That is by itself is sufficient for us to get communicated, get connected with the base station, and in turn with anybody else across the globe. Then what is it? This ultra reliable low latency communication, massive machine type communication, all these things are for. And we maybe parallelly we have discussed about this. The other domain which is growing is IoT, and now we have industrial IoT. And for those devices to get connected to the network, we need to provide a path. We need to provide bandwidth, right? So that's where this massive machine type communication comes in. Then the ultra reliable low latency communication. Suppose if you want to speak to my friend or my colleague over phone who is or someone who is in Canada or any other country across the globe, I'm not much bothered about my latency. Yes, of course, but not ultra reliable low latency. But we just think of a scenario where we speak about this robotic surgery and all those things, right? So timing is the most important thing, where the every second, millisecond is being accounted, right? So maybe a few days back, there was some news regarding this robotic surgery being done by a doctor in Chandigarh, and he has carried out some surgery for a patient somewhere in the other parts of the country. So what are the bands used? When we speak about this millimeter wave antennas, uh, first we should know why we use these millimeter wave antennas. Okay, so the millimeter wave antennas forms the part and parcel of this 5G. So for 5G, we will be using two bands. One is FR1 band, another one is FR2 band. Yeah. So we'll be using FR1 band and FR1 and FR2 band. Then for FR1 band, we have the frequency ranges 410 to 7125, and for FR2, we will be having 24.525 to 52.6. So this is called as millimeter wave. So in addition to this, maybe within this 410 to 7125, we will be using 3.5, then 4.9 GHz. It's being explored in most of the countries. For example, in India, when we speak about this 5G, we have this mid band called as 3.5 GHz that is being used in most of the 5G networks. As you could see, this band starting from 24.25 to 52.6 is called as the uh, millimeter waves. Okay, so why we call it as millimeter waves? Why we move from low frequency to high frequency? What may be the advantage? Can anyone guess? Yeah. So the reason is simple. When we move from low frequency to high frequency, we want to have high data rate, right? So it is not that low frequency offers very less data rate. Since our requirements have grown, maybe when the mobile phones were introduced in the 90s or 95, 96, in that time space, we have had our primary importance is only voice, but now it is not the case. We have data. So data have become most important, and hence we need to provide a large path for the data. That means a large amount of data is being accumulated. I want to have a seamless connectivity. I want to have a seamless call, either using any of these applications with anyone across the globe. If that is the thing we are looking for, then we need to have a larger amount of data rate. So that is possible only if you move from low frequency to high frequency. That's what given here. As you could see, it is 900 megahertz to 1800, from 1800 to 2.1 gigahertz, 3.3, and we have 26 and 30 to 300 gigahertz. And this is the band we have moved. And for 5G millimeter wave bands, we may make use of 26 to even 100 gigahertz of frequencies. And this is, so which country makes use of which band? That may be the question that comes to your mind. As you could see here, these are the millimeter wave bands released by different countries. As you could see, US, they have a different band, and in Japan, they have a different band, and Korea, they have a different band. China, they have a different band. Difference in the sense, it is between 20 and 25 or 20 and 30, but a small variation is there. For example, 27.5 to 27.5, 28.35 is one band in US, and 37 to 38.6, and even 64 to 71. So it starts from 27 and it ends and reaches till 71 gigahertz in the case of US. And whereas you could see Israel, they have a different component, and Korea, they have a different component. Japan, they have some 27.5, 29.5. This is the status, global status with respect to 5G, particularly millimeter wave bands. Then if it is 6G, so we have used high frequencies, 27.5 to 28.35, or 27 to even 60 or 70 gigahertz is called as a millimeter wave band. Why we move from low frequency to high frequency? It is to make use of the, like we are interested in large amount of data that's have to be transmitted from the source to the receiver, or between the user equipment and the base station, and the vice versa. Then what will be in store for 6G? What we are going to do with 6G then? Then this is the 6G band. It is not yet finalized, but maybe in the WRC, World Radio Conference, and they may come out with some kind of standardization. So what is earmarked? As you could see here, here 470 to 690 for 6G, and 700 to 2.6 for 6G, and we have 4.4 for 6G as well. And this is yet another band, and we have 24 to 52, and even more than 90 gigahertz is also being planned for 6G. All these things, as you could see, which is more than 28 gigahertz, 24 gigahertz, comes under the millimeter wave antennas, millimeter wave technology. So what's the difference? We have three different terminology that's being widely used. One is RF, microwave, and millimeter waves. RF, the entire component is called as RF. So the researchers across the globe, whenever we speak about RF, it comes between 10 kilohertz and 6 gigahertz. Then microwaves is 6 to 30, and millimeter wave 30 and beyond, up to 100 gigahertz. The reason why we call it as millimeter wave is that when we find the wavelength of the signal that is being used for data transfer, that will be in terms of millimeter waves. But whereas here, it is not in the range of microwaves, it will be in the like micrometers, but it will be in the range of centimeters. But just to emphasize the importance of wavelength, the people have come up with the term called as microwaves. You may have a doubt. So they should have been centimeter wave, millimeter wave, followed by microwaves, right? But here itself we will be using microwaves. All this just to emphasize the importance of the um, the miniaturized nature of the wavelength that is being used between 6 gigahertz and 30 gigahertz. Next question, why millimeter waves? So we are comfortable with this 6 gigahertz, 3.5 gigahertz, but why we need to move It is all attributed to the progress in multimedia and data storage. And that is also driven by increased memory capacity. If that is the case, then we need to have our mobile wireless devices, and that will in turn demand high data rate. Okay, so suppose if I want to see a video in our mobile phone, now it is streamed without much delay, right? All because of the increased frequency ranges. So we have used 1.8 gigahertz. Now most of the mobile phones uses different frequencies, 2.4, or even if it is 5G, we make use of 3.5 gigahertz. You just think of the data rate. If I move from 3.5 to 75 gigahertz or 30 gigahertz, definitely we will be able to receive larger amount of data. But how that is possible? Yes, we have to convert the cellular aspect. For example, like for 4G, we have used this uh, many number of antennas, right? So F1, F2. Okay, F1, as you could see, covers a larger region, and F2, you could see it covers a smaller region. If I go for millimeter waves, I may need to have 2 to 3 such base stations to cover the region what was actually covered by F1. So the bandwidth is higher, but the coverage is much reduced. We will discuss about that in the end of this session. There is a three-dimensional perspective how the bandwidth, connectivity, and the coverage and the range are being related. The satellites and radar systems, which is using this millimeter waves. For example, the DTH receivers, we make use of high frequency, right? So some cellular providers started experimenting this millimeter wave communication for establishing communication between the user equipment and the base stations. So what may be the issue? So using millimeter waves to connect mobile users is a new approach. So definitely these 5G networks uh, will help augment the existing 4G networks, but at the cost of what? And the cost will be like increased path loss. So we are going to make use of this millimeter waves that will help us uh, provide connectivity, a seamless connectivity with larger data rate, but at the cost of what? That's the next question, right? So what are the other applications? For example, here you could see the future smartphone users, VR gamers, autonomous cars will rely on these amount of data every day. For them, yes, we have to have a large frequency, large frequency signals, high frequency signals to form the part and parcel of the mobile network, mobile communications. So when millimeter waves were discussed in India, millimeter waves, the concept was discussed 100 years ago by J.C. Bose, Jagdish Chandra Bose, in UK. He conducted some research. Okay, he conducted some researches in the aspect of waveguides, horn antennas, dielectric lenses, polarizers, all those things. Okay, at 60 gigahertz. 60 gigahertz again comes into millimeter waves. That was experimented, and he has proved that 60 gigahertz and its capability 100 years back. Now, even that equipment is still in existence in Bose Institute, Calcutta. And you could see, and that is also being used for NRAO, National Radio Astronomy Observatory. And so far we are discussing about this millimeter wave. So millimeter is usually considered to be the range of wavelengths between 10 to 1 mm. So we have in a generic RF spectrum from 3 kilohertz to 3 gigahertz, we can call it as simply RF, and 3 gigahertz and above, maybe till 10 gigahertz, we can call it as microwaves, and beyond that, we'll be calling it as millimeter waves, and beyond that, 100 gigahertz, we'll be calling it as terahertz again, because that becomes 100 gigahertz. This means that these millimeter waves are larger than infrared rays, but smaller than radio waves or microwaves, obviously. So the millimeter wave occupies some frequency range. So the range is 30 to 300 gigahertz. But what is being explored is between 30 and 100 gigahertz. That is the one that is widely explored for larger data transmission across the globe. So what are the characteristics of this millimeter waves? We are used to RF. We are used to RF signals, we are used to microwaves, and now we are exploring the possibility of using the millimeter waves. So we have some characteristics. So So that promises unlicensed operation like what we use for 2.4 gigahertz. And is it applicable for all the countries? Definitely not. This is in US, and each and every country have their standards. For example, FCC of US, Federal Communication Commissions, have granted uh, the use of this 60 gigahertz without any license, and it is highly secure operation, and high level of frequency reuse is enabled. Like what we have pointed out, the millimeter waves can travel for only short distance, all because of the path loss. So what is path loss? We will discuss about that. So maybe, yeah, when we can transfer only for a small distance, then that will in turn enable us to have few more such antennas, making use of high frequency, particularly millimeter waves, without much interference. Hence, the frequency reuse possibility is there. Then this supports larger amount of data rate, right? Fiber optic data transmission possible, and it is mature technology. Much research has happened and is also happening in this domain. And this supports carrier class. I mean, the reliability, 99.999% availability is there, and that will in turn gives us very good reliability as well. Okay, suppose if I use 1 gigahertz signal to transmit data from the source and to the receiver, and if I'm making use of some 100 gigahertz signal, right? So what will be the difference? The difference is how far the signal can travel. Maybe 1 gigahertz may travel a long distance, and 100 gigahertz may not travel long distance. Is all attributed to a simple formula where you could see the EM waves, the power falls off as the square of the range. Yes, power falls off as the square of the range. That is one reason. And how did we come to this conclusion? Do we have some formula? Yes, definitely. For example, if you have two isotropic antennas, and that with that, if I want to find what is the path loss, so that can be found using this formula. As you can see, the free space is equal to free space loss is 20 log base 10 4 pi r by lambda dV. So this is an extract from a very fundamental equation. We call it as the Friis transmission equation, right? So, so from the Friis transmission equation, you will be able to extract this free space loss. So P power transmitted or power received is power transmitted, and gain of the antenna, gain of the receiving antenna, transmitting antenna, then we will be having this component 4 pi r by lambda the whole square. Yes. So that is the one that contributes to the free space. So what is this free space then? It is, if we have a signal, if it is transmitted from a source to the receiver, definitely there will be some loss. So that loss, as you could see here, will increase when I increase the frequency. As you could see, this is inversely proportional to lambda, and we do have an impact of that on the frequency as well. If I keep on increase the frequency, the free space loss increases. As you could see, the free space loss has become an important and integral component of almost all the electromagnetic wave signal propagation. For example, if I use 1 gigahertz signal to transmit data from one place to the other place, and similarly, if I use a 30 gigahertz or 60 gigahertz signal, definitely 30, 60 will experience larger amount of attenuation compared to 1 gigahertz. Now you just think of a scenario where I'm going to make use of the 60 gigahertz signal in my cellular communication. So obviously, I may not be able to reach a longer distance, a larger distance, right? So how to compensate for this? Definitely, we have to have some technology. Yes, we have one technology that is called as intelligent reflective surfaces. We will discuss about that. So this millimeter wave propagation loss factor will, in addition, will have some other losses as well. So there are absorption loss factors. We'll be having gaseous losses, and losses all because of rain in the transmission medium. Like what we experience in our DTH transmission. Suppose if if there is some rain, we may experience some amount of loss, right? We may not be able to receive the signal. You will be able to predict whether it is going to rain or not just by looking at your TV signal. The same is the case with this millimeter wave signal as well. It will also experience some amount of attenuation all because of the rain. So which frequency will attenuate more? So there is an empirical graph. I'll show that. Yeah. So these millimeter wave propagation will experience losses all because of water vapor and oxygen absorption, rain, foliage. Foliage is like it may not have the capability to penetrate through the leaves and trees, right? And that will also have some bending effect as well. As you could see here, this is the one I was referring to. These are the different frequencies, okay? And this plot gives us frequency versus attenuation, okay? For uh, a frequency of 10 gigahertz, the attenuation will be 0.004 dB per kilometer. And we have two different scenarios. One is at sea level, another one is at 4 kilometer elevation. And they have kept the temperature and pressure as constant. As you could see, when I move from 10 to 15, 13, or at even 6 gigahertz, you could see a peak, right? This peak is all because of the loss factor associated with a particular range of frequency. Here it is associated all because of the oxygen absorption. So the presence of oxygen molecules will absorb this microwaves at 6 gigahertz more compared to 9 gigahertz. And you could see even 100 gigahertz, the absorption of the signal is much lesser. Here you could see it is 10 dB per kilometer, whereas here you could see it is only 1 dB or 0.4 dB per kilometer. And you could see the water absorption is there, and that is much higher when I increase the elevation, and you could see uh, the increase or the peak values are being observed at even 300 gigahertz as well. And this helps us in coming to a conclusion to choose which frequency to communicate between the user equipment and the mobile user equipment and the base station in our mobile phone scenario. Okay, so what happens at 60 gigahertz? As you could see, while signals at low frequency bands, like what we are using now, can propagate for many kilometers, but the sonic, yes, yeah, can I proceed? Yeah, can you hear me? Can someone acknowledge?
Sir,
Hello?
hearing?
Yeah, I can hear you, ma'am. Can you able to hear me?
Yes, sir. Yes.
Yes, ma'am. Yeah. Shall I proceed, ma'am?
Yes, sir.
Yeah.
Yes, sir.
So these millimeter waves can be used to establish more densely packed communication links. So that means when we go for low frequencies, the signals, for example, 2.4 or 3.5 can penetrate the buildings. And that is one reason why we receive the signals even we are inside the home or inside the office. But that may not be the case when we use of 60 gigahertz. We may want to confine our signal transmission within a building or within a room. So that much amount of confined communication is possible with the help of 60 gigahertz. So millimeter waves in turn provides a densely packed communication link. So we can have an antenna that can transmit signal only in a given 10 cross 10 or 20 cross 20 room. That fit possibility is there. So that will also enable frequency reuse, and in turn the advantage is being the capacity. So that will help us the transmit the data in terms of gigabits per second. Here you could see the challenges that when we make use of millimeter wave or millimeter wave communication using this millimeter wave antennas is that high loss, human shadowing, non-line of sight propagation will be there, but that will in turn lead to some multipath fading. Doppler shift will no more be negligible. That is, we need to make we have to consider that as well. In addition to that, there will be some noise. So this uh, figure helps you understand the impact of the foliage or human shadowing at high frequency. As you could see, if we have two antennas distanced only just 4 meter, and if I'm going to make use of 60 gigahertz signal, as you could see for direct communication, we have had a minus 35 dBm, right? So this is the frequency versus receive part. Okay, this is measured in terms of dBm. Then when I make use of a similar 60 gigahertz channel, and if you have, just for understanding, if you have less number of people and human shadowing is there, as you could see, this is a scenario too. You could see how much reduced the power is. It lies in the range of minus 60 dB, and it does much reduce to even 70 dB for more number of people between the antennas, right? But if I make use of a multipath, okay, if there is a non-line of sight communication, as you could see, the signal level have improved from minus 80 to minus 40 or even minus 45 dBm. So this is how the 60 gigahertz channel will perform in the indoor scenario. Okay, if this is the case, what can we do? So we have to come up with some kind of solution. So we can use a 60 gigahertz signal, but I don't want to have n number of such antennas. So I need to have a technology. The technology that is being explored across many researchers is this IRS, intelligent reflecting surfaces. So like uh, the 10 gigahertz to 70 gigahertz, and that is experiencing all these issues like path loss, atmospheric and rain absorption, and low diffraction and penetration through objects. So for which a new technology is being used, that is IRS, which has the potential to overcome the poor propagation effects. So what we are going to do, we are going to increase the signal coverage and we are going to reduce the energy consumption. That means we are achieving something called as increased signal coverage at the reduced energy consumption. That is, we are concentrating on power efficient technique, power efficient spectrum utilization. So what is this IRS? It is a meta surface. As you could see here, a simple pictorial representation. As you could see, we have some uh, array of structure. Each and every component is called as unit cell. And what forms this unit cell is the meta surface. Okay. So we form a meta surface using this unit cell, and from the unit cell, we will be able to control the phase component of the signal, what is being incident on that, and because of which we'll be able to uh, change the direction with which the signal have to reflect. So that means we have a base station or an access point that will radiate the signal from the antennas, whatever is being used, which is operating at high frequency, and that will in turn be received by the IRS, and that will be reflected, received and reflected to the desired region. Okay. So it is a passive, low cost reflecting element. So each and every element, so this is the element I'm referring to. Each and every element is a unit cell. So this will help us reflect to, they reflect the incident EM wave to the desired region. It can be here, or it can be here, or it can be reflected here. So based on the angle of incidence and the angle of reflection. As you could see, this is one IRS. Here they call it as beam steering performance of a 2-bit IRS at 6 gigahertz. At 6 gigahertz, you could see there are n number of unit cells here. Here, as per this paper, they have used some 40 cross 40 IRS unit cell elements. Then for each and every variations, as you could see, 0 degree possibilities here, and here you could see 10 degree variation in the main beam, and 20 degree variation in the main beam, and 30 degree variation. So I will be able to tilt the radiation pattern from 0, 10, 20, and 30. As you could see, there is a variation in the main beam that is being tilted. So if this is the IRS, and I'll be able to tilt to the any angle of my interest. Again, depends upon how many diodes I'm going to use. Here they are using 2 diodes, and we have 4 stages: 0 degree, 90 degree, 180 degree, and 270 degree. Okay, this is, they call it as a 2-bit intelligent reflecting surface. And here there are some standards. For example, in Europe, the band is 59 to 66 gigahertz, and in US they have 54 to 66 gigahertz, and in Japan they have 15 to 66 gigahertz, and as you could see, they have some limitations in the power aspects. 10 dBm is the maximum power that will be allowed, and the gain is only 47 dBi. Okay, then for this realization of millimeter wave applications, what may be the constraints on the antenna design? So microstrip patch antenna is the one which is widely used in realizing the millimeter wave antennas. But since we have some issue with this micro patch antennas like narrow bandwidth, right? So microwave antennas making use of this microstrip concept is much widely used, but they do have some disadvantage, that is the narrow bandwidth problem, but that is now overcome with the help of many techniques are there. L probe feed, stacked patches, U slot patch, cavity back structure, and aperture coupled feeds. And ME dipole, magnetodielectric dipole, is the new addition to this. Along by making use of any of these techniques like L probe, stacked, U slot, you'll be able to increase the bandwidth of the microstrip patch antenna. So whatever the millimeter wave antennas we are discussing, all those millimeter wave antennas comes under a simple category called as microstrip patch. So what is Bharat 6G vision? How we are going to cater to the requirements of Bharat 6G vision? So now we have the 4G and 5G is also being used in most of the cities across India, and we could see the 5G technology promises speed of 10,000 Mbps, or I could say 10 Gbps, and that makes use of this millimeter wave spectrum and beamforming concept. And what is in store for us by 2030? So, as per the information broadcasting wing of India, so maybe a few months back, there was some article that is being released. So that focuses on Bharat Vision 6G statement, where you could see by 2030 we are going to launch 6G, indigenously made technology. So 6G will offer ultra low latency, like much reduced latency with speeds up to 1 Tbps. Now we are speaking about the data only in 10 Gbps, but what we may expect by 2030 or after will be 1 Tbps of data with ultra low latency. And one more thing is that we are going to have very less power. So target efficiency of 1 picojoule per bit. If I want to transmit data between the base station and the user equipment, then what I'm going to use is restricted to very lesser power, so that the amount of power that is required by your mobile phone or the base station transfer data will be much reduced, so that you'll be able to transfer more amount of data with very less amount of energy, right? So if I could transmit a single bit with just 1 picojoule, then that is the one what we are actually looking at from 6G vision. And these are some of the use cases, as you could see. So even now we are connected, right? So everything is now connected. Even if you want to um, book a taxi, we go for this mobile phone. And if you want to go for any kind of communication, we go for a mobile phone. If you want to go for any kind of transaction, we make use of mobile phones. So everything is connected. So this 6G is going to harness this connectivity to the next level. As you could see, everything, healthcare, fire station, smart electric, so with your mobile phone, every device will be connected. Maybe by 2030, who knows, we may have a smart chair we'll be able to control whenever we are want to organize some kind of meeting in the room. We may want to draw a pattern, and according to that pattern, the chairs may align themselves. So that is by converting your chairs into something called as IoT device. So whenever a device is becoming instrument, we call it as IoT, right? And Internet of Things, right? So we convert a device to an instrument, so that will get aligned itself. And whenever I want to conduct some meeting, I can decide what pattern the chair should be aligned, or it may automatically align based on our requirement. So that is, so you can control everything using your mobile phone. That means everything is connected, right? So we make use of some of these services already. So in addition to that, we may have these many number of smart waste management, industrial hubs, and automated public transport, digital library, AR, VR, all these things will be interconnected. How we are going to interconnect? Again, 6G is the one. So if I going to have this robotic healthcare center, and if there is some delay, definitely will be of no use, right? So 6G focuses on reducing the delay, reducing the amount of data, increasing the amount of data, reducing the amount of power that is consumed for transmitting the worst case of even 1 bit. So apart from these advantages, 6G also allows for directed beam communication through MIMO. MIMO antenna is another thing that's being explored. Even if you buy a mobile phone now, a new mobile phone, you could see 2T cross 2R or 4T cross 4R. So these specifications will be there in most of the mobile phones. That means 2 cross 2 or 4 cross 4 antennas are being used. Why it is used? To transmit power beams in a specified direction. So why we need to use multiple antennas? Again, to increase the bandwidth. So I believe this 3 dimension of 6G spectrum will help you understand the importance of bandwidth versus frequency and coverage. So if you consider this is the base station, right? So if I'm going to use a low frequency, okay, a low frequency, as you could see, the coverage is much higher, okay, coverage is much higher, but bandwidth is reduced. If I go with the high frequency, the coverage is reduced, but the bandwidth is increased. Similarly, if I go with a bit higher frequency in the range of millimeter waves, I'll be able to further increase the bandwidth, but at the cost of coverage. Further, if it is in terms of terahertz, the coverage is bit reduced, but I'll be able to have increased bandwidth. So the learning is that when I keep on increase the frequency from low frequency to high frequency, so we may have the advantage of have increased bandwidth, but we have to have an eye on the coverage as well. So if I increase the frequency, bandwidth increases, but the coverage reduces. That is one reason at 60 GHz, we are more concerned about the coverage. This is the 6G spectrum, what we discussed, like 4.4 to 4.8 GHz is one that is being explored, and it is not yet standardized. And it is believed that the WRCC, so World Radio Communication Conference in 2027 and IMT 2030, that will give us some info. Standardization of this 6G will be done. So presently, all these bands are being used. 600 MHz, 700, 800, 900, all these bands are being considered or identified by the International Mobile Telecommunication for this potentially 6G spectrum. So what are six key technology if we make use of this millimeter waves, and particularly usable for 6G? And this focus on almost everything. As you could see, AI and ML is going to be part and parcel of this antennas as well. From the optimization of beamforming, like if I want to communicate a larger amount of data to a single user, we need to go for the beamforming. We make use of MIMO antennas, right? So for which we have to have AI and ML, and that will also be helpful in scheduling the calls and the spectrum. What is the spectrum I'm going to use? And we may develop a network that is going to sense where the object is, and what I'm going to do with that. For example, if I want to have the connectivity to a chunk of people where they are in need of larger amount of data, then I need to go for a beam steering or a beam forming technique that makes use of MIMO antennas. Then extreme connectivity, ultra reliable, low latency communication is required for most of the ma'am, can you able to follow me? Yeah. So extreme connectivity is required, and new network architectures are being explored. Then we have something called as asymmetrical architectures, and even the antennas are being used. Then security and trust is yet another thing. 6G networks will be designed to protect against threats like jamming, right? So this MIMO antenna is the one that is widely used. So MIMO systems uses multiple antennas, both the transmitter and the receiver. Why it is used? It is to support the increased throughput and capacity as per the requirement of the 6G. So how we are going to use, and you could see the beamforming is the key factor that is being used under this MIMO. We call it as massive MIMO, which increases signal quality by spatially focusing power, amplifying the transmitted signal as well as the received signal in a particular direction. Why we are using that? We need to increase the data rate, and also we will be increasing the signal to interference and noise ratio. And we have some 2 to 3 different types. One is spatial multiplexing, as you could see here. The multiplexing is done where several data streams are multiplexed in same time frequency symbol. So we make use of single user MIMO and multi-user MIMO. As you could see here, each and every color denotes different type of data, I mean different type of symbols that is being transmitted. For example, in single user MIMO, it is a central component of massive MIMO. As you could see, one user, okay, multiple beams are being sent from the antenna to the user. This is a single user MIMO. But whereas we have something called as multi-user MIMO, I have to serve for 2 to 3 different users, for which we make use of it is the same base station, but that provides service for all the users. But you could see the colors, okay, different colors are there, right? So that is each and every beam. Okay, so the multiple layers are transferred to different users across the spectrum, and to yeah, so they do have different requirements, right? So to satisfy the requirements, we need to transmit the data from the same base station, but different antennas. We have to make use of the MIMO, multiple input, multiple output antennas. Okay. So what is installed for us? So we discussed about millimeter wave antennas, millimeter wave concepts, and millimeter wave technologies, right? And the most important thing is like this power. The requirement for power is being increased. Okay, so how to address the power requirements? All by making use of conventional, non-conventional modes. And yet another thing that is being explored by people across the globe is the solar castles. So can I have a constellation of uh, gigantic satellites, and that will in turn collect the sunlight and convert that into uh, the usable energy by making use of PVs, and that will confine the same energy to the people on the earth. Is that possible? Yes, that is possible. As you could see, this is the representation, or you could say the idea behind the construction of solar castles in the sky. So this can be considered as the solar castle, and that's going to communicate, confine the sunlight onto a photovoltaic panel, and that will convert that into a electric energy, and that will be made to propagate using the microwaves, and that will reach the earth segment, and that will be used uh, so the required applications. Okay, so the thin film reflectors track the sun, concentrate sunlight onto a earth facing energy conversion array that has PV panels, and that will in turn make use of microwave antenna. Here you could see again we make use of microwave antennas, and that will distribute the power for the required applications. Here the systems from the PV panel to the earth segment is making use of microwaves. So these microwaves, the band that is being much widely explored is 2.45 or 5.8. It is not new technology, and there are countries that have explored this, and they have demonstrated this as well for low power communication. And by coming to 5G, if the 5G is going to make use of millimeter waves, then we need to have more number of base stations. Like 5G have limited coverage. So if I want to increase the coverage, and I have to have more number of base stations, right? So if that is the case, we may have more number of base stations than what we have now. So how to uh, uh, proceed with this 5G? But we are in need of data. I need to have ultra reliable communication. I need to have power efficient communication. All these things are possible by one technique. I need to increase the base stations. Okay, but what can be done? So an organization in Japan have come up with a technique where the transparent antennas are being used. So they have used the windows. Okay, these are uh, the organization's windows, where they've converted that windows to antennas. They etched the antennas onto the glass, because here the glass is going to act as the substrate. Okay, so deployment of new glass antenna. As you could see, it converts the window into a base station, and that will in turn provide the service to the users uh, proximity to that particular region. Okay, this is one technique where people are making use of the glasses as the transparent antennas by making use of some etching technique where you can convert a glass into an antenna. So that will in turn provide some coverage to a particular region. The next thing is this IoT and energy scavenging. Since we speak about this massive machine type communication, that means we are going to add more number of devices, right? For example, if we consider IIoT, industrial IoT, if I'm going to measure what is um, the absorption, what is the health of a motor. So I may want to deploy some sensors, right? Those sensors have to be powered up. I need to check the health of the sensor as well. So how to power up? We may not just like that uh, leave the nodes once it's being deployed. We need to provide the battery source or use some kind of energy, right? So now people are eyeing upon something called as WPT. WPT is wireless power transfer. So there, wireless power transfer. So we have this near field solutions that is being launched and that's being explored widely. Okay, the new technique is by making use of far field solutions. So the far field solution is that, so we have an antenna. So that antenna is going to provide the required information. That is, we call it as information decoding. And will it be possible for me to have a setup that will receive the signal and that will in turn power up my battery? If that is the thing, then we can call it as energy harvesters. So wireless energy harvesting components. It is not wireless simply power transfer. We are going to harvest that energy. We have the wireless chargers. So we are not bothered about the charges. Here we are more bothered about how can I make use of the ambient electromagnetic signal to power up my device. Okay, so they call that as simultaneous wireless information and power transfer. That is called as SWIFT technology. So using the SWIFT, simultaneous wireless information and power transfer, you'll be able to receive the signal as well as you'll be able to power up the device. Maybe in another 5 to 10 years down the lane, we may have mobile phones, and those mobile phones we may not be that may not require periodical charging. Instead, it will directly charge or it may charge its battery, power up its battery once you start using the signal for receiving the data. So the same signal may be used to power up your device as well. Okay, so it may not 100% power up, or it may help us sustain the power for some amount of time. Okay, so these are some of the techniques that's being explored. So this is all about the millimeter waves and its advantages. So yeah, so with this, I would like to close the session. Hope the session was interesting. If there is any queries, there are any queries, yes, the forum is for people to discuss, share. If you have any queries, yes, you can ask. And these are the references. And yeah, so if you want to reach out to me, you can make use of this.
Participants can ask their questions in chat box. Okay, I think there is no queries. Thank you, sir. You have expertly explained the challenges, opportunities, and future research directions in the way system, making complex concepts easy to understand, highly relevant. The session has truly enriched our technical knowledge and inspired us to explore advanced wireless communication technologies. On behalf of EC department, we essentially thank Dr. Ram Prabhu for his valuable time, insights, and engaging facility. Thank you, sir.
And we will be having some discussion on some design and analysis of some special type of wearable antennas using both flexible substrates and rigid substrate. And we'll be having a session on recent researches and the last is a conclusion. I hope everyone knows about antennas, but these wearable antennas are exclusively a different topic because this is what we are using for on-body application as well as off-body application. So first we can see what makes this wearable antenna different from conventional antenna. So that is that. Then only we can go for the further things. So this is unlike conventional antennas. This wearable antenna should be efficient and reliable because we are using this wearable antenna mostly for body worn application. That is, it can be worn by a human being or can be integrated into clothing. So that can be like a smartwatch, or it can be an accessory, or it can be a biomedical device for measuring the vital signs. So here, the research on wearable antennas is progressed because we are hoping for a future where patients can receive medical advice from the comfort of their own home without no need to visit the hospitals or no need to take the prior appointments, no need to have be in a bigger queue. So with this wearable antenna, we can measure all the vital parameters of the patient, and by harnessing the power of viral communication, we can use this as a battery driven one, and we can monitor the patient's status and can be informed to the doctor nearby. So by using these type of gadgets, wearable electronics or wearable devices, it is very easy for the people to run, especially the bedridden people, to avoid the frequent hospital visits. And here we need to discuss about the wearable antennas. So here in wearable antennas, usually we are focusing on a compact, lightweight antennas, and that has to be designed to operate while being worn on human body. Or it can be integrated into clothing. Or it can be an accessory like a wristband, or it can be with any biomedical device. So it can be of any form. So here, we can say the wearable antennas play a major role in BAN. I hope everyone knows what is BAN. BAN is body area networks, and WBAN, that is wireless body area networks. So this enables the applications like health monitoring, fitness tracking, military communication, emerging services, and smart textiles. So now the question comes, as we already discussed in the introductory part, why we need this wearable antennas. Just the answer is very simple, just to make our life simpler and easier. Just to make our life simpler and easier, this wearable antenna is usually of two types. One is implantable antennas and another is on-body antennas. So on-body antennas means it will be a part of conformal clothing, and implantable antennas is something that is mounted inside the body. So there are two types. So here I am going to discuss about the antennas that can be a part of your clothing. So here we know that with the advent of this medical technologies, now so many surgeries are successfully done by implanting cardiac pacemakers, cochlear implants, and intraocular implants. So all these devices are purely electronic devices which uses implantable antenna sensors. So first, before discussing the theoretical concepts of this wearable antenna, first of all, I need to make you aware that these antennas are not only used for just transmission and reception. It can be used as a sensor also. Right. So when anyone is asking you what is an antenna, everyone used to say antenna is used for transmission and reception. It is true, but it can be used as a sensor also. So in cardiac pacemakers or cochlear implants, usually we are using implantable antenna sensors. So that antenna can be acted as a sensor as well as can be used for its conventional transmission and reception. And when we are considering the operating bands or operating frequencies, usually we are using this wearable antennas at ISM frequency, that is 2.4 gigahertz, and we are using this for ultra wideband as well as for emerging 5G bands. And here the now we are going to the conclusion of what are wearable antennas. Wearable antennas are nothing. It is a flexible, lightweight antennas that can be integrated into clothing or accessories worn on the body. And here we can say it will be just as a part of your clothes. It can be just like an embroidery in your clothes, or it can be just like a flower shape in your shirt, or it can be a design in your pocket. So no one will not be able to identify that is an antenna. So it looks like a part of your clothing. And as we are using the wearable antennas, mostly we prefer flexible materials or the conductive fabrics. So usually this wearable antennas are fabricated on the basic principle of patch antenna. So we know that the patch antennas are made up of substrate, ground, and a patch. So as we already know, the substrate is a dielectric material and the patch and ground are conductive material. So here for inflexible antennas, we can, so in
Ma'am?
wearable antenna, hello?
Ma'am, sorry to interrupt.
Yes, ma'am.
The screen slides has not been shared, ma'am. It is showing only the title slide.
Oh, it's, I changed, it's not showing. 1 second, ma'am. I'll reshare, ma'am.
Okay.
For me, it is changing. That's why I thought. But it's showing your screen are sharing. You are screen sharing. Like
The first slide is shown.
okay, ma'am. Ma'am, or I'll do one thing, ma'am. I'll share my PPT with you. You just share from your side.
Okay.
Huh? Shall I stop sharing, right?
Yes, ma'am. Yes, ma'am. Please share it.
Okay. I'll stop sharing. And by the time, if you want, I'll share the PPT.
Antennas.
What, ma'am?
Yes, right.
Okay, okay, ma'am. I'm not keeping in full screen.
You
Just
can handle.
I'm keeping like this alone.
Yes, okay.
Okay, sorry for the discontinuity. So here we are discussing about the wearable antennas. So as we already discussed, these are flexible and lightweight antennas, and it can be a part of your conformal clothing. So we can stitch, either we can stitch or we can paste this in your clothes. So here usually we are using flexible and wearable antennas usually from flexible substrate. Mostly we are using some conductive fabrics, or we are using some paint, or we can even implanted this under the skin. So that is purely another category of antenna. It is called implantable antennas. Here we are not discussing about any implantable antenna. We are discussing about the antenna which can be a part of your clothing. So it can be a wristband, it can be a bangle, it can be a chain, it can be a pendant, or it can be a button in your cloth, or it can be a embroidery in your shirt, or whatever it is. So what we are discussing here is a part of your conformal clothing. And when we are discussing the scope, so here we can say that this mainly we are using this for fitness tracking, health monitoring, then military communication. So when we are discussing about the military application, usually we are using this wearable antennas for live tracking. That is, this will be worn by a soldier. Maybe he will be keeping this on his helmet or on the body, on pocket or somewhere, and just to track his position, whether that soldier is alive or not. So that is one of the applications of this wearable antennas. And here When we are discussing about the wearable antennas, usually we would have seen that so many devices with smaller size. So obviously, the one of the challenges in this wearable antenna design is miniaturization, because we are in need of some smaller size devices, because since we are using this and we don't want to dispose this to anyone else, so then the device should be of smaller size. So that is one of the challenges in designing this wearable antenna, because it should be of a miniaturized size and it should be operated in multiple band of frequencies. Then only it can be used for multiple application. So these are the usual challenges and scope of research. You can do the research by pointing out these challenges. And when this, as we already said, this compact antenna, it's an integrable part of wearable devices. So here we are focusing on some performance parameters. So here we are usually implementing the antenna designs based on bandwidth requirement and efficiency, electrical performance, polarization effects, size, and application of the wearable device. So here, when we are discussing the basic antenna parameters, we know the basic antenna parameters are its electrical performance, then its polarization effects, its size. All these constitute the antenna performance. So here also we are focusing the same, like the conventional antenna, and usually we are using some technologies to design wearable antennas. Usually we are using microstrip antennas, microstrip technology, and we are using printed dipole antennas as this wearable antenna. Then similarly, we are having monopole, slot antennas, and PIFAs. And here, this is the basic structure of a microstrip patch antenna. So in microstrip, as I already said, we are having three layers. The gray color layer, what I have shown is the substrate, and the top one is the patch, and the downside also we have the same yellow color, that is the ground. So here I have given this patch and ground with yellow color because the both indicates a metal. So the patch and ground should be a conductive one. And the substrate, as we already said, it is a dielectric material. So we already know that dielectric material is characteristic. So here we will be discussing the challenges in wearable antenna design. So wearable antenna, as we said, it should have a close proximity with human body because it is worn by the human being. So when an antenna is worn by a human being or it is placed on a human body, we need to consider two things. One is the effect of body on antenna as well as the effect of antenna on body, because we will get radiations, right? So body is a near field, is being in near field. So that results in detuning of antenna as well as it gives some harmful radiation to our human body. So the two things we have to keep in our mind, one is the proximity to human body, that will affect in two ways. One is the detuning of antenna, and that is the some back radiation to human body. And see here we are using keeping antennas of higher efficiency for this sensor application. So that requires a longer, that requires more battery. That is, we won't be getting more, we will be getting a shorter battery span. And the next is the flexibility. So here for meeting these challenges, what we are doing is so that addressing these challenges will be other scope of the research. So uh, when we are discussing the first challenge, that is the impact of human body on wearable antenna as well as the impact of wearable antenna on human body. So we can first consider the first scenario, that is the impact of human body on wearable antenna. So we know that our human body is made up of two by third of our body is water, right? So our body is having several tissues, muscles are there, some flesh is there, and we have blood. So blood contains water. So see all these layers, that is skin, tissues, fatty layers, then blood. So and muscles, all these things are having its own permittivity, right? So when we are considering an antenna for on body application, that means we are keeping the antenna on our body. Suppose I'm keeping the antenna on my wrist. So that wrist part is having flesh, blood flow will be there. So obviously water content will be there. So all those permittivity values will get added up and constitute an effective permittivity. So this effective permittivity, so I said the substrate is a dielectric material and the dielectric material is characterized by permittivity. So all these, the permittivity due to our body will get added to the permittivity of the substrate. So in short, we can say an effective permittivity will be generated there. So this effective permittivity may result in the change of antenna operating frequency because we are designing the antenna based on the permittivity. So when the permittivity value changes, that may result in the detuning of antenna. So that is the one case. So when we are designing an antenna, we have to consider all the body permittivity parameters, right? The next thing is the impact of electromagnetic radiation. We know it's nowadays it's very common to talk about the radiations. If we are using an antenna closer to the human body, definitely there will be an electromagnetic radiation. Impact of electromagnetic radiation will be there. So in such cases, we need to do some measures. We have to take some measures to avoid the impact of this electromagnetic radiations into our body. So that is the second one. And nowadays we know that for on-body application we have to clear one test, that is for specific absorption rate. So for all our mobile phones, everything it has to maintain some specific absorption rate value. So here these impacts, that is of impact of human body on antenna and vice versa, is the major challenge in the design of wearable antenna. So all these can be done by the correct choice of substrate, then dimensions and all some extra care that we have to provide during the fabrication of these wearable antennas. So next slide. So now here we have a comparison between the wearable antenna and conventional antenna, the wearable and traditional antennas. We know that we are keeping the antenna at some place and we are taking all the measurements, but here we have to take the on-body measurements. So here also we have to analyze all the parameters like return loss, gain, directivity, radiation pattern, efficiency. Along with that, we have one more term that is called specific absorption rate. This usually called as SAR. And that gives the appropriate value, and that gives the value that defines whether this antenna is harmful to the human body and vice versa, right? And the next is next thing what we have to consider in the design of antennas, bending effect. So as it is worn by a human being, our human body has several curves. So we have to make it in such a way that it should, when the body, if I'm keeping it on human arm, in the diagram itself, it is very clearly shown. If we are keeping an antenna on our arm or on our leg, so there will be a chance of bending. So when the antenna gets bent, definitely it will change the electrical length of the antenna and results in the antenna detune. So that is the next parameter we have to consider while designing the wearable antenna, that is the bending effects. How the antenna performs on a bend. That is the one important thing. And when we consider the next point, as the time is shorter, I'm just moving fastly. So the next thing what we have to discuss is about specific absorption rate. So the specific absorption rate is up. Actually, our government suggested to provide the specific absorption rate for each gadget at a permissible level. Usually, we are taking the SAR value less than 2 watt per kg. So if this value is below this 2 watt per kg, then only the particular gadget will get sanctioned or will get licensed, right? So this is the safety. For our safety purpose, we have set this rule. So the specific absorption rate is can be calculated for each electronic gadget, and we have to ensure that it should be it should be less than 2 watt per kg, right? So that is another important parameter related to this wearable antenna, that is specific absorption rate. So now we are considering the different types of wearable antennas. So as I already said, we have two types. One is the textile antenna. In textile antenna, we are using some conductive fibers and can be woven into the clothing. So we can stitch that conductive fibers into the cloth. And the next is inkjet printed antenna. So we can just draw some lines or tracking using this some designs using this print. And the next is the implantable antenna that is subjectively placed inside the human body. So usually we are using the implantable antennas for cardiac pacemakers and for some brain sensors, some brain activators also we are using. And the next is, ma'am, kindly change the slide, ma'am. Methodology, ma'am. You can skip next slide and you can go to methodology. So this is the basic methodology in designing the antenna. First is the selection of design parameters. So first of all, we have to decide on what type of material we have to make this antenna. I can make an antenna using a cloth. I can make an antenna using a rubber substrate, using a plastic. So whichever material is compatible for our human body, we can choose, and then we can model the structure using any simulation tool. So for that, usually we are using high frequency structure simulators. That's usually called as HFSS, or we are having CST through CST also. And we are having different types of tools are available nowadays. Even we can use MATLAB for simulating antenna structures. And once the simulation is over, we'll be doing the fabrication and testing. So the testing can be done at anechoic chamber. In the anechoic chamber, we are doing the testing. And the final thing is the comparison and the validation of the project result. So this is the thing, the design procedure. First, we'll be doing the material selection. Then it will be doing the material characterization, because the material selection is very, very important, because the permittivity of the substrate and the dimension of the substrate, dimension of the patch, everything decides the antenna performance. So all this is the design procedure. So we'll be starting with material selection, material characterization, then antenna design, simulation and optimization, antenna fabrication, and antenna measurement. And the next is choice of substrate. So the choice of substrate can be done in two ways. Ma'am, kindly change the slide, ma'am. Choice of substrate can be done in two ways. One is we can have a flexible substrate. We can like cotton, jeans, or we can have lycra. Then next is the non-textile. Example is paper, Velcro. So here we are having two categories. One is flexible substrate and another is non-flexible substrate. So we have to find the compatible substrate to embroidered logo antenna. In this, I have made this using the substrate jeans. So it looks like a jeans. Actually, I have done it in the pocket, jeans pocket. So exactly the jeans pocket I have taken, and the substrate permittivity is measured as 1.6, and I have a structure of 90 bar, 70 bar, 1.57. And here I have given the copper sheet at the ground, and the copper is the radiating element.
and it's of thickness 60 microns, and I have used a 50 ohm microstrip line. And here the feed length is 1.6 mm, and the feed width is 1.6 mm, and the feed length is 17 mm. And here I have kept BTU in the patch. So the BTU is drawn by removing the copper material from the patch, and in this I have used the principle of capacitive coupling. So so we know that the antenna is also an RLC circuit, it's a resonance circuit, so RLC circuit. So if we add or remove the metal from the antenna, that may result in the capacitive coupling or the inductive couplings. Here I have provided the capacitive coupling, and here I have used some adhesives non-woven on the non-woven conductive fabric. So I have used a adhesive that is free of this permittivity change, and these are the design equations. So in this design equation, it can be seen that the width, effective permittivity, and length. Ma'am, you can go to slide number 26. Hello, ma'am. Am I audible? Hello? Hello? Hello?
Ma'am, you're audible, ma'am.
Am I audible?
Yes, ma'am.
Okay. Okay, ma'am, you can go to slide number 26, ma'am. 25, 26. 25, you can show the diagram, then immediately you go to 26, then immediately move to 27. Because I'm taking only half a minute for each slide. Just show the antenna structure 25. Slide number 25. Yes. Yes, this is the antenna, logo antenna, embroidered logo antenna, and the following are the design equations. The next slides, 26 and 27 are design equations. So here, go to slide number 29, ma'am. So this is the this slide shows how this can be used for the measurement of bending effects. So I have measured this for considering the bending effects. So because this is a body worn antenna, so I have kept it on a cylinder and calculated the bending effect at 45 degrees as well as at 60 degrees. Ma'am? Hello, ma'am? Hello? Slide number 29. So for this testing, I have used for testing the effects of bending, I have used a cylindrical shaped polyethylene foams, and the foam material of the cylinder does not affect the surface currents of the antenna. So the bending the antenna changes the effective length, which ultimately changes the resonance frequency as well as the return loss values. So here mainly we have done the return loss measurement. You can go to slide number 31. So here we can see the results. So the return loss has been measured, and in this, for different angles, the return loss is different, showing different, because we can see the bandwidth also getting changed on different bending angles. So, so we have to consider all these changes while designing the antenna, and we have to make sure that at different bending angles, even though the bandwidth changes, we have to make sure that it should work at the appropriate frequency range, or the antenna should be operating at the required frequency value. And see in the next slide, 32, slide number 32, you can see at the last diagram, this is simulation output at 90 degrees, at 90 degrees of bending angle. See, at 90 degree, we can see the antenna shows an unstable characteristics. That means this particular antenna is suitable only for bending up to certain levels. Beyond that, it won't perform like an antenna. So this is not suitable for bending beyond 75 degrees. So, so this is the next slide is the bending analysis report. So you can see at 0 degree, it has an S11 return loss of minus 21 dB and the bandwidth of 250 megahertz. And at 35 degree, we can see a change in S11 value as well as the bandwidth is getting reduced. And at 75 degree, it also it works quite well. And at 90 degree, it was unmeasurable thing and it shows an unstable characteristics. And when we go to the next parameter, so from this we can conclude that the antenna changes its effective length when the antenna is bent. So the bending on the antenna increases the results in the decrease of effective length and change in return loss, resonance frequency, and bandwidth. This is very, very important thing. So when the antenna is bent, the electrical length gets decreases, then the return loss changes, and when the return loss changes means that the resonance frequency also shifts and the bandwidth also changes. And the next thing is slide number 35. That is the setup for SAR measurement. So SAR measurement is done by checking the antenna on body. So here we are not in real-time application. We are not directly measuring on body. So in that we will be making some phantom model. There will be mimicking the exact human body there by using some flesh, blood, and all those permittivity levels. So that by mimicking that, we'll be measuring the value and we'll be seeing what is the impact of this antenna on human body. And we have to ensure that the SAR specific absorption rate should be less than 2 watt per kilogram. So usually in our mobile phones, we are having 1.77 watt per kilogram. So that is why we are able to use a mobile phone in our country, not in the country or over the globe. So this, if it is greater than 2, it cannot be commercialized, right? So the next is this is the slide number 36. The next is the fabricated structure. So you can see the exact antenna on a jeans fabric. So here it looks like a jeans pocket. So here this antenna was fabricated in 2015 or 16. So that time we were not having that copper tapes or all those things. Now we have more flexible copper tapes are available, so we can just need to stick. So here I had used a copper plate. So that is why the bending results gone worse. So if I have used a copper tape instead of this copper plate, definitely the bending effects would have improved much. So this is the test results. So here I have kept this. This is the vector network analyzer. This is to check the S11 parameter, and VSWR also can be measured. This is the VSWR, and it is for antenna. The VSWR value should be less than 2. And here, this is the setup for measuring the radiation pattern. So this setup is called anechoic chamber. Here, we are using a horn antenna as the transmitter and our antenna under touch as the receiver. And we'll be sending the transmitter will be sending the signal, and the way in which the antenna is receiving the signal will be measuring the radiation pattern. And see, this is here we have done the measurement for both on body as well as off body. And the antenna directivity and gain, and it shows a better gain of around 2 to 3 dB. And these are the radiation pattern. And this is another type of antenna. This is the paper antenna. This is the latest one. Here we have used the tapes, copper tapes. Instead of copper plates, we have used copper tapes. And we have connected the SMA connector in between the point, right? So this is more in total, this is a highly flexible one. And the previous one had some limitations because of copper sheets. So the next is the wearable antenna using non-flexible substrates. So here we are using PTFE taconic ceramic, FR4, RT Durol, plastic. All these are non-flexible substrate, but here, if we are doing this for a miniaturized structure, for a smaller structure, then it won't get affected in any ways due to bending effect. But here, when we are choosing a material, we have to be careful that some materials are not suitable for our body. So materials like FR4, plastic are not compatible with our human body because it may cause some harmful effects on human body. It's a single band cuff button antenna. So it can be used as a button in our normal clothing in a shirt. So this is in this I have used a PTFE taconic ceramic and the permittivity is 10 and the diameter is 22.3 millimeter and operating frequency is 2.4 gigahertz and substrate height is 3.1 on 8 millimeter and the radiating surface is of copper. And see, this is just look like a button. Here, I have used a rectangular shaped substrate, but I have given the filleted edges. I have given the filleting at four sides, making it to look like a normal button. So these are the design equations. I'm not getting into detail, and these are the design parameters. So I have taken the patch, substrate patch, everything is based on this parameter. Here, as I already said, the substrate is a square shaped one, and the patch is a circular one. And just for getting the shape of a subject, I have done the edge filleting. And this is the fabricated structure. See, it is having the size of a small, having the size of 1 rupee coin. And I have done this is the measurement setup using VNA. And here, this is the structure that can be used for 2.4 gigahertz for medical application. The next one is a slotted ring resonator based multi-band button antenna. So this can be used. This is a multi-band. So this will be operating at 3 frequencies. And so we can use this for multiple applications at the same time. So especially in military application, where we can assess the soldier fatigue assessment and battle management and for any other vital parameter, or we can use for radar communication because this antenna used to resonate at 3 frequencies. So this is the basic structure. And here I have given the slotted ring resonator method. So I have provided the slot that also in turn a type of capacitive coupling provided here. And because of the capacitive coupling, that the RLC parameter got changed and that results in the change in resonance frequency. Here the permittivity of 10 is used and the same material PTFE taconic ceramic is used and diameter is of 22.3 millimeter. And we can do the research with more body-friendly substrates like silicon, or we can use some conductive in circuits. And because these are body-friendly materials and it won't cause physically potentially any harm to the human body. And so we can switch on to using these type of materials. And the silicone and all usually looks same as that of the body part. And so we can do the research with new materials. And here we can use another thing we can use with the help of some 3D printing. Here we can go for some complex shapes and structures. And here, just here we are using for if we are supposed to use this for biomedical application, this is just to monitor the glucose levels and just to avoid the invasive testing. Invasive testing means if we want to measure sugar or diabetes, we have to make a pin prick. Like we have to put a needle and we have to take the blood and we have to measure. But with the use of wearable antennas, we can find the glucose level by measuring the change in permittivity. So see the patients who are having diabetes having different permittivity, their blood is having different permittivity than the others with normal sugar level. So that change in permittivity definitely will result in a change in resonance frequency. By measuring the change in resonance frequency of the antenna, that frequency shift, we can diagnose that whether the person is having the sugar or diabetes or not. That is one of the applications. And when we are coming to the another set of applications here, we are using these antennas as an ideal partner for small radio devices, mainly for military applications. So here, for military applications, usually we are focusing for multi-band antennas because it can work on multiple frequencies. So now we can see the antenna can be used as both transmitter as well as both transmitter and receiver, and at the same time it can be used as a sensor also. So sensor, no need to buy another sensor because we can make the antenna itself as a sensor. And here we are using antenna sensor for measuring the temperature, dielectric, and the mechanical crack, everything. So the single antenna can be used for, see here, for measuring temperature, we are using one set of sensors. For measuring dielectric, we are using pH sensors, gas. So many things are available, different varieties are available. And for this mechanical part, we are having the sensors too. Antenna can be used as a sensor to measure the shear and strain, pressure, etc. And when we go to the next one, these are the different structures. And these are the common list of previously reported work of flexible antenna textiles sensors. You can see that these are the different types of things, and the sensing parameter in all these things they have mentioned as frequency shift. So in only one it is mentioned as specific absorption rate. So usually in all biomedical application, we are using this antenna as a sensor by sensing the antenna resonant frequency shift.
Participants, kindly
So this
unmute
is
your
the
mic.
So this is the last slide. So here I'll be showing this is an AI based. This is a recent research topic, AI based wearable antenna system for biomedical application. See here we can incorporate this wearable antenna. We can combine wearable sensors with some machine learning process, and we can do the visualization as well as the dashboard. Here we can get it connected to the mobile or web. So the so many parameters, vital parameters can be measured and can be informed to the healthcare specialist. So these are the three steps. One is three stages. One is the design of wearable sensors, and another is the machine learning process. So the machine learning will be doing all the feature extraction, feature analysis, feature extraction, classification, and predicted feature. And from that, it will be provided to the visualization part, and from there, the answer will be generated and will be informed to the healthcare specialist. If we are discussing the future scope, so the contribution of low profile structure can be incorporated into smart antenna technology, but which uses the tuning methods, and we can extend this for supporting MIMO applications. So now we are usually doing this for the normal application. So single input, single output application. Now we can extend it for MIMO application. So multiple parameters can be done simultaneously, and we can implement these wearable antennas much in wearable devices to open the way for non-invasive health assessment. And these are here by improving the precision and efficiency of current manufacturing and measuring methods. Here we can introduce new conductive fabrics as well as the conductive fibers, and all those things can bring a better wearable antenna for biomedical application. And this is my conclusion. And if you have any queries, you can ask. Thank you.
Participants, if you have any queries, you can put it in the chat box.
Yeah, check the chat. So you can ask directly, you can have an interaction, you can have a conversation, or you can raise the question in the query also, in the chat box also. See, if anyone is doing research in this wearable antenna, you can choose some topics related to this, and you can combine AI with this, and you can make it suitable for biomedical applications. So that is a trending one because the biomedical is getting it's a booming technology. So if you're doing any research in antennas, just you can switch, you can combine it with biomedical application.
Okay, sure. If you want to have any collaboration in future, we'll be contacting you with the wearable antennas.
Yeah, sure,
Thank you,
ma'am.
ma'am. Thank you for your
Yes.
valuable time and sharing your knowledge for the FDP session, today's session. Thank you very much, ma'am.
Oh, okay, thank you, ma'am. First of all, I want to ask sorry for you for the inconvenience caused from my side due to the network connectivity issues. I'm so sorry for that, and I thank everyone, especially the organizers, for inviting me to give such a platform. And if you have any queries, you can contact me at any time. I'll share my mail ID in my chat box. In the chat box, you can take and you can contact. Right?
Okay,
Sure,
ma'am.
ma'am.
Sure.
Sure.
Okay. Thank you.
Thank you.